For decades, black holes existed entirely as a mathematical quirk. They lived purely on chalkboards and in the margins of relativity equations, invisible, dense voids that physicists assumed we would never actually be able to see. That changed in 2019, when a synchronized global network of observatories called the Event Horizon Telescope captured this image. A blurred, glowing ring of gas framing a dark center, the first actual photograph of a black hole. Astronomers also found a way to map them closer to home. By observing the center of our own Milky Way, researchers tracked dozens of stars moving at extreme velocities, locked in a tight orbit around a highly massive, completely invisible object. Long-term mapping like that relies on Earth-based observatories, utilizing massive twin telescopes perched on a dormant volcano to pierce through the cosmic dust and watch the galactic center in real time. But observing these objects in the real world has created a massive problem. The way black holes actually behave is actively breaking the established rules of both cosmic history and quantum mechanics. The standard model of the universe dictates a strict chronological order. Expanding gas cools to form stars. Those stars cluster together to build early galaxies. Eventually, the most massive stars run out of fuel and die. That stellar death is a violent event. The core collapses inward, creating a stellar mass black hole. Over billions of years, those small black holes merge and gradually grow into supermassive ones. Recently, the James Webb Space Telescope looked deep into the ancient universe and found an object that shatters that timeline entirely. Pointing at a tiny, underdeveloped galaxy called Abell 2744 QSO1, Webb detected a black hole weighing 50 million times the mass of our Sun. The anomaly is the timeline. This black hole already existed a mere 700 million years after the Big Bang. This animation highlights the problem of scale. The central black hole is vastly oversized compared to the sparse stars orbiting it. A galaxy this young has not had enough time to birth, kill, and merge enough stars to create a black hole of this magnitude. The math of the old model is physically impossible here. Instead, data suggests these supermassive black holes formed within the first moments of the universe. They did not grow inside existing galaxies. They were there first, acting as the primary gravitational anchors that built galaxies around them. While telescopes scan the deep universe, theoretical physicists are facing an even tighter mathematical crisis at the microscopic scale. It started when Stephen Hawking proved that black holes aren't completely black. He demonstrated that they slowly leak a tiny amount of thermal energy. Over unimaginable stretches of time, this Hawking radiation causes a black hole to steadily shrink until it eventually evaporates into nothing. That evaporation process triggers a direct conflict with the rule of unitarity, a strict law of quantum determinism. Unitarity states that the unique physical details, or information, making up a specific piece of matter can never be permanently destroyed. This chart shows the collision of these two facts. If a complex object falls in, and the black hole eventually evaporates into random, featureless waves of ambient radiation, the object's unique, defining information is erased. If data is deleted like this, leaving a completely empty void, our foundational mathematical equations fail. Without information conservation, we lose the ability to predict the future or reconstruct the past. This is the black hole information paradox. It is the exact point where the unbreakable laws of gravity and the unbreakable laws of quantum mechanics fatally contradict each other. To prevent the laws of physics from breaking down, theorists are having to invent radical new models to save the universe's data. This graph illustrates the leading mathematical proof, known as the page curve. It charts the entangled entropy of the radiation. It shows the entropy increasing until it hits a peak, the page time, and then returning to zero. This mathematically proves that the information escapes, but it fails to explain exactly how it escapes the intense gravity. To provide that mechanism, physicists are proposing entirely new physical geometries. The leading idea argues that the event horizon is not an empty threshold. Instead, it is a tangled, dense structure known as a fuzzball, which stores information on its surface and encodes it into the outgoing radiation. Theorists are willing to replace a smooth, featureless singularity with a tangled ball of cosmic string. That extreme compromise proves that physicists will completely rewrite the physical anatomy of a black hole to keep quantum mechanics intact. The Webb telescope found a failure in the macroscopic rules of how gravity builds galaxies. Simultaneously, Hawking's radiation theory exposes a failure in the microscopic rules of how information is preserved. These are two separate symptoms of a single problem. Our current rulebook for gravity doesn't agree with our rulebook for the quantum world. Physicists do not view these paradoxes as scientific failures. They treat them as highly specific signposts, pointing out exactly where our current models of reality remain incomplete. Merging these two contradictions into a single mathematical framework leads to quantum gravity, a model that functions at both the galactic and the subatomic level. We used to think of black holes as cosmic garbage dumps, dark corners where the rules of physics simply stop working. Today, we understand them as the universe's most important laboratories. Researchers today use black holes as stress tests to reshape our conception of space, time, and the very fabric of reality. At these coordinates, we aren't just watching a star die, we are watching our current understanding of the universe evolve.